Hello everyone. In the previous video, we discussed about some of the basic concepts of plane, and we did derive a formula for one point form of a plane. So in this class, we will be discussing about determination of a plane. So majorly a plane in 3D can be determined by one of the three following combinations. The first type is a plane passing through 3 points. So I've already defined a plane over here. It's x plus 2y minus 3z, and yeah, it is passing through the origin also. So what we'll be doing is, let's try to place 2 points over this plane. Okay, let's place 2 points A and B. So now what I'm going to do is, I'm going to pass a line through the two given points A and B. So I do have a point here. So let's see what if there is another point at the same line. Okay, and let's try to see if we can actually find out a plane which is passing through these 3 points. So plane through 3 points, and those 3 points are C, B, and A. So if you see, that is not defined. So the reason is already been discussed in the last video. So that there could be infinitely many planes passing through this particular line. So it will not uniquely determine this particular plane. So if you want to uniquely determine this particular plane, then you might have to define a point which is other than the same. That is basically a point which is not in the same line. That is three non-collinear points. Now let's see if we can figure out a plane which is passing through these 3 points. And that is going to be the same plane whatever we started with. So this is a plane which is passing through this BAD. So this is a plane BAD. So there is a unique plane passing through these three given points, provided these 3 points are not collinear. And if you see, on connecting these 3 points, we get a triangle, which is a plane figure. And that is the smallest plane figure we can actually draw, polygonal plane figure. And on extending all the sides indefinitely, we can generate a plane. If you see, not just see, any point for that purpose which is in the line will never determine the plane. It always determines the line in which both A and B are there. Okay, on varying the point C, we can actually determine the line but not the plane ABD itself. Now let's try to generate an equation of a plane passing through three given points. Let the points be A, B and C, where A is given by x1, y1 and z1. B is given by x2, y2 and z2. And similarly C is x3, y3 and z3. Okay. So we already learned the 1 point form of a particular given plane. So that if suppose we are considering this particular point for that 1 point form, then the equation of the given plane which passes through A, B and C is going to be A times x minus x1 plus B times y minus y1 plus C times z minus z1, which is equal to 0. Yeah, which is equal to 0. Now what we know is, since these 2 points also lie on the same plane, right? So since these 2 points also lie on the same plane, they should satisfy this particular equation. So wherever x, y and z is there, if I substitute x2, y2 and z2, the equation is going to be 0. Similarly, wherever x, y and z is there, if I substitute x3, y3 and z3 in those three places, the equation will be again satisfied and the resultant will be 0. So those equations will be A times x2 minus x1 plus B times y2 minus y1 plus C times z2 minus z1 is going to be equal to 0. Similarly, we have A times x3 minus x1 plus B times y3 minus y1 plus C times z3 minus z1 is going to be equal to 0. So now what we have here is three simultaneous equations. On eliminating A, B, and C, we can actually express them in the following determinant form, in this particular form. So that is x minus x1 by x2 minus x1 by x3 minus x1, y minus y1, y2 minus y1, y3 minus y1. And the last column is z minus z1, z2 minus z1, z3 minus z1. This whole determinant equal to 0. So we can just substitute the values of that point. So we have the point A, x1, y1, z1. We have the point B, x2, y2, z2. We have the point C, x3, y3, z3. On substituting the values here, we do have one variables, that is x, y, and z. So substituting those points here, we can actually generate the equation of the plane just by these three given points which is lying on the plane. So there are two direct type of questions which is following this equation of plane passing through three given points. One is they might give you the 3 points which is lying on the plane, and they might ask you to find the equation of the plane. So that is what we were discussing before this. And the second one is, instead of giving 3 points, they might give you 4 points, and they might ask you to show that all these 4 points are, sorry, it's not collinear, it is actually coplanar. So all the 4 given points are coplanar. So when I mean coplanar, that means all 4 points lie in the same plane, right? So for that, it's quite easy, just 2 steps. So if there are point A, B, C, and D, so you first create the equation for these 3 points. Yeah, you have to create equation for these 3 using these 3 points. So you would have an equation of the given plane. And we also know that this point D also lies in that particular plane, right? So on substituting the values of x, y, and z coordinates of D in the equation which we have created, and if it is being satisfied, then we have proved that the given 4 points are coplanar. That means the given 4 points lies in the same plane. Moving on to type 2. So we will be given with the perpendicular distance of the plane from the origin, and we'll be calling it P, and the normal vector to the plane. Yeah. So let's see how it's going to look. We have our 3 dimension over here. So I've defined a plane which is not passing through the origin in this case. Yeah. So provided we know that the distance from the origin to the plane, provided that distance is perpendicular distance. When I say perpendicular distance, we could even measure the distance from here to here or here to here. The reason we are measuring the perpendicular distance is that is the smallest distance from the origin. Smallest distance between the plane and the origin. So what I'm going to do now is define a normal vector, but let's just take a unit perpendicular vector itself. So it's asking us the plane. Let's give equation 1. So we have a perpendicular vector from the origin. It's a normal vector, but for the case of derivation, we'll be using a unit vector which is in the direction of a normal vector to the plane. That's why we're considering a unit vector now. So we just need the normal vector and the distance from the origin to the plane. With just these 2 conditions, we should be able to determine our plane. So let's try to get the vector form of the equation using the perpendicular distance from the origin to the plane and the normal vector to the plane. Okay, so here we have a plane. So with the 3 axes, the plane cutting across that. Let's say the point or the point where the shortest distance meets the plane is n. Okay, and obviously our origin is going to be O. The distance from O to N, let that be called as P. Okay, that is the distance from the origin to the plane. That is a perpendicular distance. Here is P. Let's take some random point on the plane. Let's call that to be R. Okay, so the P here is the distance from O to N. We're taking a random point R, and the position vector of R is going to be OR. And we can consider this particular triangle which is there in the space. Okay, so let n vector be the unit vector in the direction of on vector. Okay, but since we know the distance from origin to that particular n is p, we can express our on vector as the distance p, sorry, the distance p times n vector. Okay, and here we can actually see there are three vectors, right? OR vector, ON vector, NR vector. So we can actually represent our OR vector as ON vector plus NR vector, right? I can express this like this. Also, NR vector can be rewritten as OR vector minus ON vector, right? Let's call the position vector of R to be R vector. So R vector be the position vector of the point capital R. So our NR vector is rewritten as OR vector, that is the position vector. We are going to represent it with small r vector minus, we already know what is ON vector, that is P times N vector. So I've rewritten NR vector over here. So if you see, this NR vector lies on the plane, right? And also I know that ON vector is perpendicular to the plane. So since NR vector is lying on the plane, that means ON vector is perpendicular to NR vector also. That is, ON vector is perpendicular to NR vector. So from the dot product definition, ON vector dot NR vector should be equal to 0, right? So we already know what is ON vector. Our ON vector is this one, and we had rewritten it as PN vector, right? And we already know, we have just derived for NR vector using the vector addition, that is R vector minus PN vector. So one thing which we have to keep in mind in the starting is, we should start this with the condition that P is not equal to 0. So we are considering the distance from the origin to the plane is not equal to 0. So we are defining for such kind of planes. So looking at this entire product is going to be equal to 0. So since P is a distance, P cannot be equal to 0. P cannot be equal to 0. That means the rest of the thing is going to be equal to 0. So let's just multiply this n vector inside. So we have r vector times n vector minus p times n vector dotted with itself is equal to 0. So since this is a unit vector, this value becomes 1, right? So now we are only left with r vector dot n vector, n cap vector, minus p is equal to 0. We can also rewrite this as r vector times n cap vector is equal to p. So we have generated the equation of a plane using the perpendicular distance from the origin to the plane and the normal vector. So this is called equation of a plane, equation of a plane in normal form. So since this is involving vectors, this is the equation of a plane in normal form in terms of vectors. So this is a vector form of this one. Obviously there is a Cartesian form also, which we'll be doing next. So this is r vector times n cap vector is equal to p, is a vector form of equation of plane in normal form. Now we'll be doing the Cartesian form of the previous equation. So let's say the coordinates of R to be x, y and z. Then we can represent the position vector of R as xi plus yj plus zk hat. If suppose L, M and N are DCs of our n vector, n cap vector, then we can express our n vector as Li plus Mj plus Nk. Substituting them in the vector equation, we have xi plus yj plus zk dotted with Li plus Mj plus Nk, that is equal to P, right? We know in dot products, the components of i's get multiplied, components of j's get multiplied, components of k's get multiplied. Let's see what happens. So on multiplying, we get nx plus my plus nz is equal to p. So this is a Cartesian form of the equation of the plane. Cartesian form. So where x, y and z are the coordinates of points in the plane, L, M and N are the DCs, that is the direction cosines of the unit vector n, and P is the perpendicular distance from the origin to the plane.